Okay, so the plan for today is to finish Bayes' theorem. We have one last example to do in there, and then start chapter 6 on continuous probability distribution. So we have a few supplements on Bayes' theorem in the supplemental materials folder, and also I opened up a chapter 6 supplemental materials folder with some supplemental problems. Again, just problems if you want a little extra practice. They're not to be handed in for a grade or anything like that. And also the normal distribution table is in there, which we may or may not get to today, but we'll definitely be working with tomorrow and for a lot of the rest of the course. So check that folder out if you haven't already. Just a reminder, the Examity practice exam is available. The Unit 2 exam isn't until the week of November 11th, but good to get the Examity system kind of set up, make sure everything is working well. I was just working on it just before class now, so I'm planning to hopefully by the end of today or tomorrow, but at the latest by Friday, uh, post a more extensive breakdown of exactly how to log on to Examity, log on to MyStatLab, get the two connected and all of that. Students have been having a little more trouble with it this semester than in past semesters, and I think there are just a couple of things that folks are doing, just not reading certain pages carefully and so on, that are causing a little bit of friction. So if you're struggling with getting the Examity system up and running, my number one recommendation would be make sure that you actually read the user guide that is linked in that announcement, that you watch the video that is linked, and that you read the pages that come up on Examity. So when you click like start exam and there's a pop-up from like in the Examity website, like actually read it. Don't just, I see in the recordings people just click next really fast and then they don't know which buttons to click or what to do or where to go, because that's what all of those pop-ups were instructing them what to do. So uh, but yeah, so that's available. You can work through that now, or you can wait another day or two, and I should have some more extensive instructions uh, posted. So if you want more of like just follow this list of, I think it's about 11 things, you can go that route. If you're more comfortable using the technology and kind of reading it step by step, Examity says do this, then do this, and Examity says do this next thing, do this next thing, and so on, you can just jump right in. But overall, I haven't seen very many tech problems with Examity. It's mostly the kind of just making sure the things are, uh, understood well. Unlike ProctorU, where we do have legitimate tech problems, and that's the reason we're using Examity for the rest of this semester. Okay, and then the quote of the day by Dave Ramsey, a financial guy. One of his quotes is "Desperation precedes stupidity." Um, if allow yourself to be in a situation where you're very desperate, if for instance, we have an exam coming up, um, if you keep pushing off studying for the exam or reviewing the material or whatever, and you get right up to, the end, near the end of the exam window, and you know, that's pressuring you to make worse decisions, right? It's easier to make better decisions when you're not under pressure. So, you know, choosing a course of action where you minimize the chance that you'll be under pressure, like for instance, planning to take the exam a few days early rather than say Sunday night, that just uh, makes it much easier to make high quality decisions. So that was our quick quote of the day for today. Okay, so back to Bayes' theorem. So this was Bayes' theorem. Remember, we could kind of think of this philosophically in two ways. We could think, well, we have a conditional probability of A given B, and sometimes we're given information that's more like probability of B given A, and it would be nice if we could flip that condition. We, of course, know that probability of A given B is not the same as probability of B given A, so we can't just flip the condition and call it equal, but we have to flip the condition and multiply by the ratio of probability of A over probability of B. So that was kind of the frequentist way of thinking about it. The perspective we're going to take here, and I think the perspective that we took in the first two examples as well, is a machine learning example. So we're through these three examples, we've been kind of taking the perspective, the philosophical perspective. The frequentists would not disagree with the math; they would disagree with the philosophical statements. But in examples 1 and 2, we said kind of a general member of the population, or maybe the specific person, has a certain risk of a disease based on what we know about them right now. We get a little bit more information, maybe a test result. Tests aren't perfect. So whether the test is positive or negative, it's not going to be a guarantee that the patient has that disease or does not have that disease based on the test result. So we don't want to just say, okay, the test result is the only thing that we're going to go with, and we forget about everything else in the past. But we also don't want to just ignore the test result. It is a new piece of information. So how do we systematically incorporate that information to update our worldview, to update our estimate of the probability this person has the disease, right? If the test is positive, the probability of having the disease should probably go up relative to before they had a test that was positive, but it shouldn't be 100%. And likewise, if the test was negative, the probability of having the disease should go down. That's a point of evidence against having the disease, but it's not conclusive. It shouldn't go down to 0. Our example here has to do with a car insurance company. So this is obviously a very simplified model, but our car insurance company has, we know that we have 3 types of drivers in our model. We have good, moderate, and bad drivers. And we know that of all drivers on the road, 30% of them are good drivers, 50% are moderate drivers, and 20% are bad drivers. We also know a bit about the behavior of these different driver types. Good drivers get in, and this is a table of accidents per year. Good drivers get in 0 accidents per year, 65% of the time. So about 2 out of every 3 years, they will have gotten in 0 accidents. They get in 1 accident per year, 35% of the time. So about 1 out of every 3 years, they get in an accident. And they get in 2 or more accidents, never, 0% of the time. Moderate drivers, 45% of the years that they drive, they get in 0 accidents, 45% of the years, 1 accident, and 10% of the years, 2 or more. And bad drivers, the percentages are 30, 40, and 30. So we know something about the kind of overall population of drivers, the proportion of good, moderate, and bad, and we know something about their behavior. So if I look at a particular driver and I examine their behavior over a sequence of years, maybe I can kind of dial in whether I think that they are a good, moderate, or bad driver, right? So as I accumulate more evidence about this driver, at first I don't really know anything about them, but after a year, I'll know how many car accidents they got into. If they got in 0 accidents, that is a little more concordant with them being a good driver than a bad driver. Or if they got in, say, 2 or more accidents, that's a little more concordant with them saying being a bad driver than a moderate driver. So I can look at my experience with them after 1 year and maybe update my estimate that of the likelihood they're a good, moderate, or bad driver. And then I could watch them another year, a second year, update it again, and then watch them a third year, update it again. And as this information keeps rolling in year after year, I keep updating my estimate that they are a good versus moderate versus bad driver. And of course, the kind of end result of all of this is we want to charge them a premium that's kind of in line with what their expected cost is, right? Good drivers get in fewer accidents on average, so they tend to cost the pool less money, right? The way that insurance works is you have a whole bunch of insureds, a whole bunch of drivers in this case, paying money in. Basically, that money goes into something like a collective bank account. And then when somebody needs money, when they get in an accident and make a claim, they pull money out of that bank account. So the good drivers aren't pulling very much money out because they're not making lots of claims, they're not getting in a lot of accidents. They should be expected to contribute a bit less, whereas the bad drivers are pulling a lot of money out, they're getting in lots of accidents. They should be expected to contribute more to the pool to offset they're higher cost. So insurance isn't like free money. When you make a claim to the insurance company, you're basically, asking maybe 3, 4, 5, 10 other insureds who didn't make a claim, you're asking them to give you their premium. And then likewise, whenever you have a good year and somebody else has a bad year, you pay your premium to them. They ask for your premium and you effectively hand it over, right? So everybody pays money into the pool and then they take money out of the pool uh, to pay for the claims. Okay, so the first question that we might want to ask to kind of set up our model is, okay, let's suppose we have a brand new driver walks in the door. Now, of course, our model doesn't take into account what type of car you're driving, what your age is, what your previous experience is. We're supposing that this person comes in, we're not interested in modeling age or car type or anything, and we don't have any previous experience with them. So a new driver walks in the door, says, hey, I want you to write me a car insurance policy. What premium should we charge them? Any thoughts on this? So some people might say, well, let's just charge them the bad driver premium because that way we're covered. We cover our bases, right? If they're a bad driver, we're okay with that. If they're a good or moderate driver, well, we make a little bit more money off the top. They pay a little more into the pool than they take out. So we're okay with that. That would be maybe nice in some sense. That would be the most conservative way for us to approach it. But the problem is we have to operate in a market. And if we tell them 250 and they go down the road and somebody else can offer the policy at a lower rate and still cover their bases just fine, they're going to take all of our market share and we go out of business. So we have to offer them a reasonable premium. We can't just say, I'll offer you a really high premium, take it or leave it, because they'll just leave it. So we might say something along the lines of, well, I mean, a moderate driver is kind of the median, both in the sense of being kind of like in the middle of the pack here, good, moderate, and bad, and also being at, say, the 50th percentile, right? Whoops, what happened there? The 0% through 30% is taken up by good drivers, and then 30 to 80% is taken up by moderate drivers. So 50% is kind of right in the middle there, the 50th percentile. So kind of the median is moderate drivers. Maybe we just charge them 125. And this isn't a bad approach. This is the approach that some people would take. It's not a bad approach, but it's lacking in one small detail. That if we just choose the median, really our pool is kind of the sum of all of the premiums. So we really would like to choose a measure of center, which is what the median's getting at, but a measure of center that's related to something like the sum of premiums, or in this case, maybe say a weighted average of premiums. So the kind of maybe conceptual shift here is, instead of looking at this driver and saying, okay, this person is either a good driver, a moderate driver, or a bad driver, they're one of the three. I don't know which one, so maybe I'll guess they're a moderate driver because that's in the middle. We can shift our thinking and say, okay, if I have 100 new drivers, about 30 of them are going to be good, 50 moderate, and 20 bad, but I don't know which 30, 50, and 20 are which ones. So I can actually take this one individual driver and kind of think of them as like 30% of them is a good driver, 50% of them is a moderate driver, and 20% of them is a bad driver in some sense, right? I mean, they are either a good, moderate, or bad driver, but I don't know. So I kind of say my degree of belief that they're a good driver is 30%. My degree of belief they're a moderate driver is 50%. My degree of belief they're a bad driver is 20%. And I'll use a weighted average of the premiums with those probabilities. Across, say, 100 insureds, I would have 30 good drivers, and I would want those 30 individual people, in a perfect world, if I was omniscient, if I knew exactly which 30 they were, I would tell them to pay $75 each. That's kind of slicing like vertically in a sense, like I'm taking these 30 people and setting them aside. But I could like slice horizontally, not in a grotesque way, but I could take 30% of each person and have that 30% of each person pays $75. That way I still get 30 whole lots of $75 just spread evenly among all of the insureds. And same with 50 lots of 125 and 20 of 250. So that's the approach that I'm going to take. My premium, I'll call it premium 1, P1, premium for year 1, is going to be 0.3 times $75 plus 0.5 times 125 plus 0.2 times 250. And I did restart my computer and try to get my calculator back up and running, but it's not wanting to cooperate. So we'll be using Excel for our calculator today as well. So 0.3 times 75 plus 0.5 times 125 plus 0.2 times 250. So the premium is 135. We can use a built-in Excel function. So let's actually do that. We'll have our good, moderate, and bad. Their premium would be 75, 125, and 250. And the probability 0.3, 0.5, and 0.2. And we actually just recognize this as a probability distribution. And what are we computing here? The premium for year 1. Well, we're just computing the expected value. So we can use the built-in function sum product, SUM product, and array 1 here. We select our premiums and hit comma, and then select our probabilities. This will multiply across and then add down, and that gives us our 135 for the premium. And let's actually code in bad driver as being 1 minus the sum of the other two. And Excel always does this to me. I swear, I don't understand Microsoft. Like, how do you have such a big company and your products just don't work? There we go. It like puts like the white space from the box above it, so you can't really select the cell above it very easily. But just little glitches like that I don't know. I feel like this Office 365 or 360 or whatever it is doesn't it feels more glitchy than whenever you could just download the product and have it on your computer. I think they worry maybe a little bit less about quality control because they know that they can just go out and kind of patch it as needed. But anyway, so if my probability of being a good driver increases, if the insurance company, after watching my driving behavior for a couple of years, if my probability of being a good driver, say, goes up to 0.5 and my probability of being a moderate driver goes to like, 0.45, then I see that my premium has gone down, right? And I think this is something that we would want to happen, right? That if we think it's more likely that you're a good driver, you pay something closer to the good driver premium, right? If it was like 0.99 and 0.01, so I'm really pretty sure you're a good driver. You might be a moderate driver and you're certainly not a bad driver. You pay basically just the good driver premium. Or on the other hand, if I think you're probably not a good driver and probably not a moderate driver, but probably a bad driver, you end up paying pretty close to the bad driver premium. So this seems like a pretty good strategy, right? So 0.3, 0.5, and 0.2 are the numbers that we were actually dealing with here. They gave us the premium of 135 for year 1. Now the question is, let's suppose that, so we offer them this policy at 135 a year. It's a competitive rate. They are happy with our policy, with our company, so they go with us. We insure them for a year, and we see that after that 1 year is over, they made one claim for one accident. And we would like to take our prior information about this person. We were kind of 30% confident they were a good driver, 50% confident they were moderate, 20% confident they were bad. We have a new piece of information that we've observed their behavior for a year and they got in one accident. And getting in one accident is maybe a little bit less like a good driver, maybe a little bit more like a moderate to bad driver. How does that extra piece of information update my probabilities? So my priors, probability of good, 0.3, probability of moderate, 0.5, probability of bad, 0.2. And I want to compute posteriors. My posterior probability is probability of good given, I'll just say 1. By that, I mean that they got in one accident on year 1. I want to incorporate this new piece of information that I've observed that they got in one accident in year 1. I want to incorporate that into my previous structure. So I don't want to just forget about my priors and, just, I don't know, take something like uh, these numbers as proportions, 35 to 45 to 40 or something like that. But I also don't want to dig in my heels and just stick with this forever, because if this person is a good driver and, if a person who's a good driver goes a bunch of years and doesn't get in any accidents and I'm still offering them insurance at $135, well, somebody down the street is going to say, no, your stats suggest you're a good driver. We can offer you a lower price and we can be more competitive. Right. So we want to compute probability good, moderate, and bad given one accident. So we'll update our probabilities. We'll plug those updated probabilities into our probability distribution and get them an updated premium for year 2. So when we come back to them for the following year, we can say, okay, based on our previous experience with you over the last year, in addition to the kind of overall population, we crunched all these numbers and your premium will go up or will go down or will stay about the same, whatever it may be. Okay, so I want to find probability that they're a good driver given they got in one accident in year 1. Well, I know that this table up here, say this number, for instance, is probability of getting in one accident in a given year, given that they're a good driver. It's a 35% chance. So my condition is the reverse of what I want. Well, that's fine. I use Bayes' theorem. So I flip the condition around, probability of good given 1 equals probability of 1 given good times probability of good over probability of 1. If you ever get confused what goes on the top and what goes on the bottom, remember that we got this by looking at, for instance, probability of 1 and good. So these two have to match, right? Probability of 1 and good is probability of 1 given good times probability of good. So that's just from our basic multiplication rule for dependent events. Now I do know that there are 3 ways to get one accident. So the event getting in one accident is 1 and good, or they could be a moderate driver and have gotten in one accident, or 1 and bad. Well, also, I think it's pretty clear from the context, but we're assuming that good, moderate, and bad drivers are mutually exclusive. So you can't like simultaneously be a good and a moderate driver or something. So probability of getting in one accident in 1 year Well, these are mutually exclusive. So that's the sum of these probabilities. Or probability of one and good is probability of one given good times probability of good. Probability of one and moderate is probability of one given moderate, times probability of moderate, and then plus probability of one given bad times probability of being a bad driver. These conditional probabilities are what I get from the table above, and the probability of good, probability of moderate, and probability of bad that are by themselves, those are our priors. Okay, so what's probability of one given good? Probability of getting in one accident given they're a good driver is 35%. What's probability of one given moderate? That is 45%, and one given bad is 40. And my prior to this previous year, prior to this new piece of information that I have about them that I'm trying to incorporate here, their prior probability of being good is 0.3, or let's just call that 30%. We'll put that here and there. Their prior probability of being moderate driver is 50%. And their prior probability of being a bad driver is 20%. So I'm just kind of treating the percents in both of these factors as though they were units, and then they just kind of all divide out. So probability of good given one accident. Well, my numerator is 35 times 30 divided by my denominator is 35 times 30 plus 45 times 50 plus 40 times 20. Want to make sure that whole denominator is in parentheses so that I'm not doing like 35 times 30 over 35 times 30. That would, what would that give me, like 900 or something like that, if I didn't put any parentheses here. And then adding on all of these, we want to make sure this whole thing is in parentheses so that it's all in the denominator. And that's whether we're doing this on Excel or calculator, doesn't matter. But this gives me about, say, about 0.26. So my probability of being a good driver, given I got in one accident in the first year, is about 26%, down from about 30% before that 1 year with the one accident. Right, getting in an accident is a little bit less like the behavior of a good driver. I need to do the same thing for probability of moderate given one, but nicely enough, remember I've said before that in any of these Bayes calculations, our numerator will just be one of the terms of the denominator. If I want to switch good to moderate to get probability of moderate given one accident in the first year, well, that just switches this and this to moderate. Probability of one on the bottom is still the same. I still have the same breakdown for probability of one. It still breaks down into these three terms. But my numerator is now just probability of one given moderate times probability of moderate. It's just this middle term, 45 times 50. So what is probability of moderate given one? Well, it's exactly this same calculation, except for my numerator, instead of choosing the first term of the denominator, the probability of one given good times probability of good, I'm choosing the second term, probability of one given moderate times probability of moderate. That's the one that I'm putting on top. So I put 45 times 50 over that same denominator. or that's about 55%, or let's say, yeah, 55%. We'll round to 2 decimal places. And then I could go through the calculation again for bad, or I could just subtract from 1. So I have 0.26 here, 0.55 here. Oh, and when I type these back in, I hard-coded probably a bad back end, but 0.26, 0.55, subtracting those from 1 gives me 0.19 as probability of bad. So these are my posteriors for year 1. At the end of year 1, when I look back and I take into account that new year's worth of information that they got in 1 accident that year, and I take that into account along with my previous information, the knowledge that kind of the population overall has this breakdown of good, moderate, and bad drivers. I bring all of that together, and this is my updated probability distribution. Little less likely they're a good driver, little more likely they're a moderate driver. Their chance of being a bad driver is about the same as it was before. We actually see their premium stayed pretty much the same, right? So they're paying something that's a little more like the moderate driver and a little more like the bad driver and a little less like the good driver, but their premium didn't change very much. So the probabilities changed around a little bit, but premium didn't change. So going into year 2, they would pay 135.75. This is probably per month, right? So per month for their car insurance. Now, what if their second year they had a good year and they got in 0 accidents? Again, getting in 0 accidents, if I look up here, that's a little more like the behavior of a good driver. It's a bit like the behavior of a moderate driver, and it's not very much like the behavior of a bad driver. This is probably going to shift this person's or our point of view of this person, our perspective of them, more towards being a good driver and more away from being a bad driver. So I would expect that my updated after year 2, my updated probability of them being a good driver is probably going to go up. It's going to go from 0.26 up to a higher number. And their probability of being a bad driver is probably going to go down, going to go from 0.19 down to probably a lower number. And the effect that has on their premium is they get to pay a smaller just not having good luck with these tables these days or today. So they would get to pay a smaller proportion of the 250 and a larger proportion of 75, and that should drive their premium down. So let's check that. Now we can think about what's happening here in a timeline. Here's like time 0. This is our 30, 50, 20 probability. After 1 year, they got in 1 accident. So at time 1, that's my, what was it? 26, 55, 19. That's a posterior for year 1. But from the perspective of year 2, well, from the perspective of year 2, this posterior for year 1 is kind of like a prior for year 2, right? It's the distribution immediately prior to when I'm going to incorporate the new information from year 2 that they got in 0 accidents the second year. So kind of for this whole year, they were paying a premium of 135. For this year, they were paying 135.75. And for this year, I don't know what it should be, but it should probably go down. Getting in 0 accidents is a good thing. Oh, I wrote my wrong thing up here. Getting in 0 accidents from time 1 to time 2. So I'm thinking of this posterior for year 1 as being the prior for year 2. So that is our 26, 55, 19 distribution. So they got in 0 accidents the second year. What's their posterior for year 2? And there's probability of good given 0, probability of moderate given 0, and probability of bad given 0. So we're chaining on one new piece of information, then another new piece of information, then another new piece of information as we get more experience with this person year after year. So what's probability of good given 0? Well, just like we saw before, that's probability of 0 given good times probability of good over probability of 0. And G's are really looking like 6s today. Now I think they even look more like 6s. So. And like before, I know there's a few different ways of getting in 0 accidents. I could get in 0 accidents and be a good driver. Or I could get in 0 accidents and be a moderate driver. Or I could get in 0 accidents and be a bad driver. Now here, when I write probably of good, probably moderate, probably bad, I'm talking about the posterior, or I'm sorry, I'm talking about the prior for this year, which is the posterior for year 1. So I'm talking about these posteriors. The posteriors for year 1 become the priors for year 2. Those are the numbers that I'm inputting in the probability good, moderate, and bad. These ones here, not the 0.3, 0.5, and 0.2 anymore. So when I'm talking prior, I'm talking prior to the piece of information that I'm currently about to incorporate. So prior to the year 2 information getting in 0 accidents, but we've already incorporated the year 1 information that got in 1 accident in year 1, as well as our kind of general understanding of the population. Okay, so what's probability of 0 accidents in a year given good driver? That is 65%, and the others are 45 and 30. So 65, 45, and 30%. 45 and 30 being for probability of 0 given moderate and probability of 0 given bad. So we see getting in 0 accidents is kind of a little more like a good driver's behavior and a little less like a bad driver's behavior, but it still could happen for any of them. Our prior probability of being a good driver is prior to this year 2 information of no accidents is 0.26 or 26%. That goes here and here. Our prior probability of moderate driver is 0.55, 55%, and bad 19%. So let's come over here and change these. I basically have to rewrite this whole thing anyway, because basically everything has changed. So I'll just delete it and start over. So I need 65 times 26 divided by, and then I need parentheses here. Make sure to include that whole denominator inside of parentheses. 65 times 26 plus 45 times 55 plus 30 times 19. That looks good. Okay. End parentheses and, oh, I forgot my equal sign. Equals. So that gives me 35.7%. Let's call it 36%. Oh. So my posterior for year two, that takes my prior for year two, which was the posterior for year one, and incorporates this new one piece of information. The person got in 0 accidents for this second year of driving, is 0.36 for probability of good. And similarly, if I want to compute probability of moderate given 0, what changes is the numerator, the denominator, all of the ways of getting in 0 accidents doesn't change. It's still all of the different ways. We're just plucking out, instead of the first term in the denominator, the one associated with good drivers, the proportion of all of the 0 accidents that also is associated with good drivers, we're plucking out the proportion of 0 accidents that are associated with moderate drivers. We're plucking out this middle term in the denominator. And I'm going to be lazy and just copy this. And instead of using this for the numerator, I want to use my 45 times 55, my moderate numbers, and I want to put those in the numerator instead. Right, so I have, instead of this, I have 45 times 55 in the numerator when I'm computing probability of moderate given 0 accidents in the second year. And that gives me about 52%. And plugging these numbers in, my probability of being a good driver went up substantially to 0.36. My moderate driver probability stayed about the same. It's kind of hovered right around that 50% mark the whole time because, you know, I'm kind of behaving, I guess, a bit like a moderate driver. I got in 1 accident over 2 years. So I kind of got in 1 accident 1 year and 0 accidents the next year. That actually kind of feels a little bit more like a moderate driver. So 0.36 for the good driver, 0.52 for the moderate driver, and subtracting from 1 gives me about 0.12 updated probability of being a bad driver. So like I expected, my chance of being a good driver went up a decent bit from this good year of driving. My probability of being a bad driver went down a decent bit from getting in no accidents that year. And that cascades over to my premium, because of course these posteriors for year 2, 36, 52, 12, those are going to be my priors for year 3. That's my best guess at this driver's status or my beliefs or whatever about this driver at this point, and I'm going to base their premium on that. My premium for year 3 is going to have gone down to 122 per month. I get to save, what was my last one? Well, it started at 135, went up by 75 cents a month because of our 1 accident in year 1, but now it goes down more than $10, right? We get to save $13.75 a month because of that 1 good year of driving, because that 1 good year of driving kind of made us look more like a good driver and less like a bad driver. We get to pay more of the good driver premium and less of that big bad driver premium. And you can imagine we could just keep going with this, right? We could keep looking at how our insured behaves over, say, this third year. We could systematically incorporate that new piece of information. We could come up with a posterior for the third year, which would be the prior for the fourth year, update their premium in light of that. And we could keep chaining this on, right? And this wouldn't be a terrible like insurance company model, right? You know, provided that we did good research and made sure that these numbers were pretty accurate, that if we did split up, you know, good, moderate, and bad drivers, where good are kind of the best 30% of drivers, moderate the next 50%, and bad the bottom 20, And we did actually make sure that we observed that they had behaviors that are in line with this table and that that was kind of consistent over time. And I feel like drivers have gotten a lot worse in the last 5 years or so. Maybe that's just confirmation bias or something. I don't know. But as long as these numbers were accurate, I think we could see that this would make a somewhat reasonable insurance model. And of course, if we wanted to say incorporate driver age as well, we could think instead of temporally going through in time, we could think kind of spatially almost that at a certain point in time, at time zero, I could start with these prior 0.3, 0.5, and time two at time or 0.2 at time zero. That's kind of for the general population. And then I could say, okay, well, given that somebody is of young age, they have maybe a bit less experience on the road. How does that new piece of information come into play? And can I incorporate that piece of information, get a posterior for the piece of information that's how old they are? And maybe another piece of information for what kind of car they have, right? That's kind of a famous like example that like, oh, if you have a sports car or a two-door car, a lot of times your insurance is higher than four-door cars. I don't know if that's true or not. It seems to make sense, but I don't, I haven't seen any actual data or read any studies that necessarily said that, but it kind of makes sense. I mean, certainly if you have comprehensive coverage on your car and your car is more expensive, the insurance company is going to want to charge you more because they're insuring a more expensive asset. So, if you have a Mercedes and it costs $10,000 to get it fixed if it's in a wreck versus a Toyota that costs $2,000 to get it fixed, they're going to want a higher premium for that. So the insurance company, of course, is in a real policy going to look at a lot more than just your driving behavior. But, I think for a simplistic model, we can see that this would kind of separate out that jumble of people at the beginning that we knew nothing about into kind of people we suspect are good, people we suspect are moderate, people we suspect are bad drivers. And I have some simulations. Maybe I'll post them on the Blackboard site that I ran some simulations and kind of showed that this does kind of separate out good, moderate, and bad drivers. Like, okay, I think it took like 10 or 20 years to get really good separation. So probably not as fast as we would like. Insurance is usually at 6-month intervals. And, you can imagine these days the insurance companies are trying to get all kinds of other data. Like they'll give you a little incentive if you like plug a little thing into your car and let it, get your car's data and, see how often you like slam on the brakes or gun the gas or drive 100 miles an hour or something. So there's a lot more information that could be gathered and could be incorporated this way. And one point that I want to note really quickly here, this is kind of a minor point. What if we had, what were we on? Second year. What if we got in two accidents in our third year? We're not going to go completely through this example or through this part of the example, but let's just, kind of look at one aspect of it. So I have some prior probabilities, good, moderate, and bad. My priors are 36, 52, and 12%. My priors for year 3 are the posteriors for year 2 at the end of year 2. And then I want to compute, say, probability of good given, not 0, 2. Good given 2 accidents in this third year. Well, that's probability of 2 given good times my prior probability of being good over probability of getting in 2 accidents. But what is the probability of getting in 2 accidents given that I'm a good driver? Well, according to our model, good drivers never get in 2 or more accidents. Probability of good given, or sorry, probability of 2 given good. Did I write that backwards down here? No, I didn't. Okay. Yeah, probability of 2 getting in 2 accidents given a good driver is actually zero under our model. This number is actually zero, not a small number, not like 0.1, but zero. Well, zero times whatever divided by whatever is actually zero. So my posterior for the third year probably would be given to as zero, but that becomes my prior for year 4. And in year 4, whatever happens, probability of good given whatever is going to be probability of whatever given good times the prior probability of being good for year 4 over probability of whatever. But now the zero that was here has jumped over and it is now here. My posterior probability for year 4 being good is zero. That'll become the prior for year 5. That zero will persist forever. So 1 year with two accidents in the same year means you can never ever be a good driver again. It doesn't matter if you get in no accidents for the next 19 years, still 0% chance you're a good driver. So that's the cautionary tale of, should we include zeros like this in models or 100% in models? Probably not. Right? A better approach might be we can make this 1%, say, 64 and 1 or something like that. And it wouldn't have this, this kind of an effect. If somebody got in 2 accidents, their chance of being a good driver would go way down. Maybe it goes down to 1%, but then after a good year with no accidents, maybe it goes back up to 3% and then up to 5 and then up to 8 and then up to 10. And right. So they can kind of climb out of the hole with enough evidence of them being a good driver after that year. But since our model is saying that it is literally impossible for a good driver to get in 2 or more accidents in a year, if somebody got in 2 or more accidents in a year, they cannot be a good driver. It's literally impossible under our model. So we want to be cautious about putting zeros or 100% into models because things like this can happen that we probably don't intend to happen. One other note here is we kept the premium constant for this scenario, but typically these premiums would adjust every year too, right? Just with inflation, like cars are going to be a little more expensive to repair next year than they were this year. The employee salaries for the insurance company and the light bill for the insurance company, the stuff that they have to pay, probably going to cost a little more next year than this year, and so on. So, this kind of premium table will typically, change a little bit year over year. And we're kind of assuming that our driver types stay the same year over year, but we could even imagine that maybe that changes year over year as well, right? The behavior of certain drivers, the chance of getting in 0, 1, or 2 or more accidents for certain types of drivers might change depending on the year, right? In COVID, not a lot of people were driving a lot of places. Maybe not many people got in many accidents, even the bad drivers, just because there weren't a lot of people on the roads. And then a year or 2 after COVID, when things opened up, everybody was going everywhere. And maybe even the good drivers were getting in lots of accidents because there's just a lot of cars on the road and a lot more chances to get in an accident. People are just driving more, right? So maybe it's less, maybe the number of accidents isn't the only thing that we would want to look at to decide whether somebody's a good, moderate, or bad driver. But, this is kind of a rudimentary machine learning or artificial intelligence, example. And this kind of a Bayesian learning system is, legit machine learning type of system. If you're interested in machine learning, there's a guy, Andrew Ng. His last name is NG. He's from, I think, Stanford. And on Coursera, he has it's Python based these days. They used to do it in in MATLAB, but it's Python these days. And He has just like a basics of machine learning, intro to machine learning course that's actually quite good. I did it years ago when it was in MATLAB because I like MATLAB more. I probably should go back and do it in Python. It would be good to brush up my Python skills, but machine learning on Coursera, if you're interested. Um, it's and you can audit it for free, just like the Excel course that I mentioned to you guys in the past. You can audit it for free and basically get access to all of the information. At least you used to be able to. I don't quote me on that today because he's his company. I think he's associated with OpenAI. I'm not really sure. There's all these different AI companies now, but his company's gotten bigger and that course has gotten a lot bigger and a lot more involved. And he's got other courses now. So um, but you used to be able to basically do everything in the course for free, even like writing up the programming assignments and submitting the programs, and they would run it on their servers and just kind of automatically verify that your program gives the output that it's supposed to. So it was a really nice course, and I did it for free, many years ago. It would be nice if it's still free, but don't quote me on that. A couple of my friends did it too, and they also really enjoyed it. So. All right. Any questions on Bayes' theorem? So what do you need to know for the course? Basically, what you need to know for the course is this idea and how to go through, say, a computation like this one or like the ones we did last time. A lot of the other stuff that I filled in around the edges, around the margins, was more philosophical. Like, how do we think about or interpret these probabilities? That's not crucial information for the course, but I think it's crucial information to understand when you're making decisions under uncertainty or trying to apply this stuff in an actual real life scenario. Now, after this discussion, we're pretty much just going to shift gears and basically take an only frequentist approach from here on out. I probably won't be able to help myself. I'll probably throw in some Bayes here and there. But the frequentist interpretation, instead of talking about, say, degrees of belief, where like one person can kind of be some strange superposition of part good, part moderate, and part bad driver, the frequentist would say, okay, this person is either a good driver or a moderate driver or a bad driver. They can't be a combination of them. They're, mutually exclusive. Pick which one you want to go forward with. And that's both a benefit and a limitation of frequentist statistics. But in chapter 7 and 8, confidence interval and hypothesis tests, we're going to be taking a completely frequentist statistics approach, which is kind of the opposite, in some sense, perspective of Bayesianism. Okay, so any questions on Bayes' theorem or on discrete probability distributions, chapter 5 as well? Any questions on any of that?
Any of the Excel files, can you put them on Blackboard, the ones from the last chapter and this also?
Yeah, sure, I can. Yeah, I mean, I've just basically been using this as a calculator. I don't know what I had typed up last time. But yeah, let me save this and what should I call it? Bayes example. Always wants me to do this stuff with the cloud now. Here, give me 1 second. I'll actually just pop it into chat so that it's easy for you to get to. If I can find it on my desktop. My desktop's a little messy right now. There we go. Ah. Zoom never likes me to share files that are currently open. I don't know why I can't just share the most recently saved version, but there you go. It's I dropped it in the chat, so it's there. Yeah, I'm basically just using that as a calculator because my Wabbit Emu, I didn't name it, that's what it's called. The emulator is for some reason glitching and not working. and I haven't been able to figure out why. Sometimes it works, sometimes it doesn't, and today it's not working. So get this set back up here. I thought I like ended the meeting or something. My Zoom window went away. There we go. Okay. Yeah, so that's in chat if you want to download that and you can reference it later on. Um, so we're moving into a new topic now, kind of related to chapter 5. We're still in this idea of probability distributions, where we're looking at kind of the opposite perspective of chapters 2 and 3, which was very empirical, was very much tied to the real world, where we said we collect some data and we, roughly speaking, estimate the frequency distribution off of data. We're now taking the opposite perspective and saying, assume we know the underlying distribution, the underlying frequency distribution or probability distribution, and maybe we want to know like what might happen on average on one run of the experiment, or what is the kind of range of reasonable values that could, reasonable outcomes that could happen in one experiment, something like that. So chapter 6 is closely related to chapter 5. Chapter 5 was on discrete probability distributions and chapter 6 on continuous probability distributions. So let's recall some basics of discrete probability distributions from chapter 5. So we had a list of outcomes, say like x1, x2, x3. This could be die rolls or number of heads on so many flips of a coin, something like that. And associated probabilities. Probability of x1, probability of x2, probability of x3, and so on. We know that, well, we know that the sum of the probabilities has to be 1, and that our outcomes have to be discrete quantitative, and that's what made this a discrete probability distribution. We computed the expected value this way. We take the products of the outcomes with their probabilities, their associated probabilities, and then we add that together. And we said we can kind of model this as kind of a mass balance system. We have a massless rod, and the xi's are locations, and the probabilities represent masses. And if this is the case, then the expected value represents the balance point. We could call it X bar for a balance point. I think that's what they call it often in physics, but we don't really want to call it that because we have X bar already meaning something. It means the sample mean. But this is the expected value of X. This location here, where if I put a fulcrum there, things would balance. It is crucially important that the sum of the probabilities is 1, because otherwise we'd have to divide by the sum of the probabilities here to get a weighted average. Okay, let's shift gears a little bit. Let's kind of think back to chapter 2. We went into a population, we took a sample, and then we organized that sample in a frequency distribution. So maybe I'm looking at, for instance, heights of people. And if the thing that I'm measuring is a continuous quantitative variable, then I have to group, right? So I could have a class that's like, whatever, 60 to 61 inches, and 61 to 62 inches, 62 to 63 inches, and so on. So 5 feet to 5'1", 5 feet 1 to 5'2", and so on down to, I don't know, what's 7 feet, like 84 inches, 84 to 85, and we're probably good after that. We probably didn't pick anybody who's more than 7 feet tall. And we have some frequency, right? basically what we're thinking is that we have our real line here, and I have like 60 to 61, and there's like kind of a bin here, right? And 61 to 62, there's a bin here as well. And 62 to 63, and there's a bin here as well. So we have all of these bins, and I grab a person from the population, I measure their height, they turn out to be between 5'1" and 5'2", and I toss their data point in this bin. So there's one more data point in this bin, and then one more here, and maybe a few there, and so on. So I toss all my data points in these different bins, and then I count up, maybe I have 3 data points in that bin, 5 in that bin, 3 here, and so on, maybe 1 down here. And that's my frequency distribution from back in chapter 2. Now, our law of large numbers says that this empirical frequency distribution that I got by sampling the population and sorting the outcomes or the measurements into these bins, that it's an estimate of the actual underlying frequency distribution, the population's frequency distribution. That if I had done this process for the entire population, that I should get something that looks a little bit like this, at least in terms of relative frequencies, right? If I took each of these frequencies and divided by n. But I could imagine coming along and saying, okay, well, I mean, in the most kind of extreme or absurd case, I could have just one bin that's really, really big that covers all of the range, and then everybody just goes in there. And I could split that bin in half and have 2 bins that are pretty big. Or I could have, like I have here, a moderate number of bins that are of a moderate size. And as I keep splitting the bins smaller and smaller, when I split a bin in 2, some of the outcomes that fell in that original bigger bin will fall into the left bin, and some of them will fall into the right bin. So when I come along and split this one in 2, some of these outcomes that were in the 60 to 61 bin will be between 60 and 60 and a half, and they'll fall in our kind of new refined left bin. It's a little smaller. And some of them will fall in our 60 and a half to 61 range in our new refined right bin that's smaller. So when I split each bin up, some of my outcomes in that bin will go into the left split bin, and some into the right split. Right, we could use smaller classes or smaller bins, say with half as much. And then our original frequency that, say, went into this bin from A to A plus 1, F1, we'd have 1 bit of that frequency that would go into the bin A to A plus a half, and then another bit of that would go in A plus a half to A plus 1. I am using closed brackets on both sides here. We're not super worried about that. That becomes a less important point a little bit down the road. But here the idea is that F1 superscript 1 and F1 superscript 2 would add together to make F1. So F1 splits into these 2 frequencies, the one that's to the left of the kind of midpoint of the previous bin, and the one that's to the right. And I could actually keep doing that. I could keep splitting my bins so that my bin width gets smaller and smaller. My number of bins, oops, my bin width gets smaller and smaller, but my number of bins gets bigger and bigger. Each time I go through and split each of my bins in half, each of my bins is half as wide. It covers half as much of the real line as it did before, but there's twice as many bins. So my bin width gets smaller, my number of bins gets larger. Because my bin width gets smaller, the number of outcomes in each bin gets smaller as well, right? If I take however many I had in 60 to 61, what did I say? That was 3. If I split that bin in half, each of my 2 bins is probably going to have something like, on average, 1.5 outcomes. Now I might have 3 and 0, or might have 1 and 2 or something, um, but kind of on average, the frequencies are going to get split in half. But really importantly, though, because so bin width is getting smaller, or sorry, bin width is getting, yeah, bin width is getting smaller, number of bins is getting larger. My frequencies are getting smaller, but my number of bins is getting larger. When I add up all my frequencies, I haven't changed how many data points I collected. I've just changed what the bins look like, how big or small the bins are that the data points are getting put into. My number of data points still stays the same, or my total frequency still stays the same. My relative frequency is always going to be 1. If I take my total number of data points divided by total number of data points, of course, that's 1. I have to add up across more bins. I have to add up a bunch of smaller numbers, but I'm getting more numbers that are smaller instead of fewer numbers that are larger, but it balances perfectly. We still have the whole time that our total frequency is 1. And this is the idea of a continuous distribution. We let our bin width go all the way to 0, and we imagine that we have infinitely many bins, each of which has like basically 0 width, an infinitesimal amount of width. Now, the unfortunate thing about doing this process is we've kind of left the realm of algebra and entered the realm of calculus. When we start throwing around infinities, we're typically in the realm of calculus. So as far as, chapter 5, we went through pretty carefully and pretty rigorously all of the algebra and all of the details. In chapter 6, we're going to be a little more hand wavy because, of course, calculus is not a prerequisite for this course. So, there will be the material that's needed to be known for Math 165 will not depend at all on calculus. I'll probably throw in a couple of little details here and there so that folks who have some experience with calculus might say, oh yeah, I kind of have something to link that to, but that's not crucial for the course. Those would be kind of asides or side notes. So in continuous distributions, we have a little bit of an issue because we have like infinitely many bins, each of which is like infinitesimally wide, and kind of in some sense, each of which contains no outcomes, even though if we add across all the bins, we get all of the outcomes. So again, it's, these kind of paradoxes are things that like the Greek mathematicians and philosophers used to be really worried about, like Zeno's paradox and things, interesting things to read up on. If you're interested, you can read about Zeno's paradox on Wikipedia or something. But so some of these things that don't seem right, it's like, how can each bin be width 0? So there's no space for any bin to include any outcomes, but somehow when we add across all the bins, we accumulate all of the outcomes. That's the magic in some sense of calculus. Not magic, it's just philosophy and logic, but sometimes seems like magic. Okay. So we also want to kind of remember that for discrete probability distributions, these probabilities were masses. We thought of them like mass. And these outcomes were locations. We thought of them like locations. So if I have, individual masses like this, I can say what the mass is and where it's located. If I split my bins, if I refine my bins further and further, I kind of don't really have like a mass anymore, but I have something that's more like a mass density. It would be like grams per centimeter or something like that, instead of just like grams. So it'd almost be like finding a balance point on, say, a baseball bat, where at some points it's heavier, at some points it's lighter, at some points it's more dense, at some points it's less dense. And, at some points it's thicker or thinner. And, where's the balance point on something like a baseball bat? That's what we're kind of looking at here, a continuous distribution where the kind of mass per unit distance changes as we go along the baseball bat. So continuous distributions, we have to represent them differently. We can't enumerate all of the different like inputs and outputs or all of the different locations and masses because we have like a smear of mass kind of across a, across a, an interval of location. So what do we have to do? Well, we have to instead talk about mass density, or in this case, remember masses are like probabilities, probability density. So in continuous distributions, we represent the distribution, the model, instead of by a chart or a table, we represent it by a graph, a drawing that represents a probability density. And of course, that graph or that drawing is, usually associated with an algebraic function that gives rise to that picture. We call these graphs or these functions probability density functions, PDFs. And that's as opposed to probability mass functions, PMFs, that we associate with discrete distributions. We never really called this a PMF, but that's really what this is. This is a probability mass function. It has a list of inputs and associated outputs. It's a probability mass function because the probabilities that we're listing correspond to masses. PDFs, probability density functions, are pictures that, or algebraic functions that correspond to densities, that correspond to kind of like smears of mass across location. And then probabilities or masses correspond to areas under the PDF. In other words, the accumulation of a mass density gives mass. If I say I have a rod that is 3 grams per centimeter, and I cut off a section of 5 centimeters of the rod, then I have 5 times 3 or 15 grams of mass. So if I have a mass density, like say grams per centimeter, I have to accumulate that over a distance, over a number of centimeters to get a mass. Analogously, accumulation of probability density is what gives probability. This has a couple of interesting results. So for instance, if X represents the height of a random Pittsburgher, then the probability that X equals 6 feet 0 inches is 0 in a continuous distribution. That's the perspective here in continuous distributions. This probability would be exactly 0. Why is that? Why is this a sensible thing to say? Well, up here, let's say instead of 6 feet 0 inches, let's just say exactly 60 inches. Well, I have this bin, right? That's like the 60 to 61 bin. And I have a few outcomes that are in there. Now I split the bin in half, right? At this point, it's discrete. I split the bin in half. Maybe I have 2 outcomes that stay to the left and 1 that goes to the right. Then I split it in half again. Each time I split it in half, I basically have a 50-50 shot for each outcome that outcome stays to the left or stays to the right of my new split. To be at exactly 60 inches, it would have to stay to the left on the first split, and on the second split, and on the third split, and on the fourth split, and on the 125th split, and on the 1,020,000th split. Every split, it would have to stay to the left every single time. Or that would be like flipping a coin and getting ahead on the first flip and the second flip and the 100th flip and the 1,000th flip and the 1,000,000th flip. I'd have to flip a coin to get ahead infinitely many times in a row. Or to get exactly 60, I would have to, each time I split this in half, I'd have to end up in the left bin every single time, infinitely many times, as my number of bins goes to infinity. And of course, that probability is going to look like 1/2, and then 1/4, and then 1/8, and 1/16, 1/32, 1/1000th after 10 bin splits, and 1/1,000,000th after 20 bin splits. That probability goes to 0, right? So as the number of bins goes to infinity, this probability goes to 0. However, a statement like the probability that we're between 60 and 61 inches, well, that's 3 outcomes out of n. That's 3 over n. Maybe I took a sample size 100. That's 3%. If I refine, then this counts up 2 bins, each of which is a 1/2 inch wide. If I refine further, this probability counts up 4 bins, each of which is a 1/4 inch wide. If I refine further, this probability counts up 8 bins, each of which is 1/8 of an inch wide. I'm still getting these 3 outcomes because I'm counting up more bins, each of which contains fewer outcomes. It balances, right? These 3 outcomes are between 60 and 61. These 3 outcomes, these 3 outcomes stay in that event. Whether I keep my number of bins, my accuracy fairly coarse, or I refine it very far, or I take it all the way to continuous, this probably doesn't change. I don't care how many bins I split 60 to 61 into. I'm still going to be counting exactly these 3 outcomes that are in these bins. I might have to count over 10,000 bins and add up a whole bunch of zeros, then a 1, and a whole bunch more zeros, then a 1, and a whole bunch more zeros, then a 1 to get my 3, instead of just saying, well, I have 1 bin with 3 outcomes in it, but I still end up with exactly that 3. So in the continuous world, now I want to be clear, it's not like illegal or nonsensical to make the statement. I mean, that's fine. An event is allowed to have probability 0. It's not like a bad statement to make, or it's not like it's wrong. In a continuous distribution, just probability x equals number always equals 0. It's just kind of boring. It's not wrong, it's just boring. So meaningful events or interesting events in the continuous world are intervals. The probability that x is bigger than a number, right? The probability that a person is like taller than 62 inches. I would count up the same number of outcomes, whether I'm counting over, whatever, 20 bins, each of which is 1 inch wide, or 40 bins, each of which is a 1/2 inch wide, or whatever. I'm counting up all of these same outcomes because I'm taking a swath of the real line. As I refine the number of bins, or as I refine my bin width, my number of bins increases, and I still count all of the same outcomes. So probability x bigger than a number, that's going to be, most likely, and most of the time, that's going to be a positive number. It's going to be a non-zero answer. Or probability x between 2 numbers, like between 60 and 61 inches, that's usually going to be a positive number. Or probability x less than a number, that's again going to be a positive probability most of the time. So meaningful events in the continuous world, or interesting events, are intervals. In the continuous world, probability x equals number is 0 all the time. Be very careful, because in the discrete world, that's very much not the case. The probability you roll a 1 on a fair die is 1/6. That's not 0. Very big difference in that regard between discrete and continuous distributions, because probability x equals 1 on a die roll, that's associated with probability mass function. That's a mass. That is a probability. But probability x equals 6 feet, that's a density. We're accumulating density over 0 interval width. That's like saying I have, a material that is whatever, 5 grams per cubic centimeter, but I don't have any of that material. How many grams do I have? Well, I don't really care what its density is. You don't have any of the material. accumulated across any space, so you don't get any mass out. Okay. So we might ask ourselves then, okay, so we have this kind of strange notion of a PDF, a probability density function in continuous distributions that has some of these strange uh, characteristics. But the PDF is represented by a function, f of x, and that function can be graphed. Maybe it looks like this. Maybe it's our classic bell curve. But f of x is not a probability, I said, right? This is a function f of x, but the outputs, the heights of this curve, the outputs of this function for a given input are not probabilities. They're probability densities. What does that mean? Essentially, what it means is this. Take epsilon to be a small positive number and take a to be a point of interest. If I go a little bit to the left of a, if I go epsilon to the left of a to a minus epsilon, and I go epsilon to the right of a, or sorry, epsilon over 2, just to make the numbers come out nicely. If I go epsilon over 2 to the right of a to a plus epsilon over 2, this gives me a whole swath of location of width epsilon. My function output here is f of a. What does f of a mean? It basically means that I can estimate the area under this curve, which would be the probability, as interval width epsilon times an estimate of the height of this curve, f of a. So that's really what the density is it is distance times density approximately gives me mass, right? If I have a bar that is 5 grams per centimeter and I chop off 6 centimeters of that bar, then I have 5 grams per centimeter times 6 centimeters, right? I have a distance times the density. I have 30 grams. I have a mass. If I have a bar that is, usually kind of about, at least around where I'm looking, kind of about 5 grams per centimeter, but maybe is a little more dense in some places and a little less dense in other places, like this one, right? It's a little higher here and a little lower there. If I chop off 6 centimeters of it, I can say, I mean, it's not going to be perfect, but I'll have about 6 times 5 or about 30 grams. And the smaller that my little chunk of bar is, the better that estimate's going to be, right? This function can vary more, it can vary in height more over a wider interval than over a narrower interval. Well, I'm not sure what I did there, but trying to get a little more space. There we go. Okay, so what are the requirements for a function to be a PDF? Can any function be a PDF? Well, no, we have two requirements. The first is that function f of x has to be non-negative for all x, and the total area under the function has to be 1. Note the similarity of these requirements to the requirements for a PMF. For a discrete probability distribution or probability mass function, my probabilities had to be non-negative and they had to sum to 1. And we have the same thing down here. The probability densities have to be non-negative. Well, if I had a negative probability density anywhere, I could accumulate over a really small interval near where that density was negative and get a negative actual probability. And that's not so good. What does it mean to say that there's a negative 20% chance that something happens? That doesn't fit into our rules of probability. Probabilities have to be between 0 and 1 inclusive. And the total area is 1. So if I had a continuous density function that was, say, constant on some interval, maybe it's from 0 to 1, if I look at the total area under that curve, to make that whole area equal 1, it's going to have height 1 as well. If this was a box from, say, 0 to 3, then it would have to have height 1/3 to keep that area being 1. Now, in a function like this that covers the whole real line, you might say, wait, how can this area be 1 when these tails go off forever? And again, the answer is kind of the magic of calculus. That's something that's beyond the scope of this course, and we'll have to be a little hand wavy about. I will give a little minor demonstration here to show you how it's possible to add up infinitely many positive things and not get an answer that's infinity. Let's consider a circle. You can think of it as like a pizza or something like that. If I divide the circle in two, and I have a line of people that want pizza, and I say, okay, well, we want to make sure there's enough pizza for everybody. I'm too lazy to count the number of people in line and slice it that many ways, so everybody just take half of what's left. If you take half of what's left, there will always be some left for everybody. The first slice of pizza is of size 1/2. The next person takes half of what's left. Half of a half is 1/4. Then 1/8. Then 1/16. And we can see we're going to keep going down the line here forever. We're adding up positive numbers, infinitely many of them. They're getting smaller and smaller as we go along. But we clearly see that this is certainly never going to be above 1, and it kind of looks like it's getting closer and closer to 1 the more of these we add on. And in fact, it is indeed exactly equal to 1. We can add up infinitely many positive things, get a not infinite result, so long as the things we're adding on go to 0 fast enough. It's not just sufficient they go to 0, like 1/2, 1/4, 1/8. They get smaller the further down we go. They also have to get small enough fast enough. These get small exponentially fast. It looks like 1/2 to the n, and that's more than fast enough for what we call convergence. So even though we'll encounter some distributions look like this that have tails that go off forever, those tails go to 0 quite quickly, and that means that we can have a whole area under the curve being 1, even though the tails go off to the left and right forever. It's a similar idea to over here. Okay, any questions on any of this so far? So that was a lot of abstract stuff. We only have 6 minutes left, and I don't really want to start the uniform distribution because I feel like it'll take 6 minutes just to get through the intro, and we won't get to the example today. But I would recommend over the, it is Wednesday already, huh? Geez, this week went fast. Over the weekend, I would recommend just kind of reviewing the intro to continuous distributions and reading through uniform distribution and a little bit about the normal distribution. Pre-read this material because, like I said, it is pretty abstract. Seeing it applied in the uniform distribution, I think, will be helpful to kind of bring some of it down to more grounding, to ground some of this in something that's more of an application. And then look ahead to the normal distribution as well, the bell curve, because that's going to be an important thing that we're going to use for in some sense in like almost every problem for the rest of the course. So I would definitely recommend pre-reading a little bit this weekend, as well as knocking out that Examity practice exam if you haven't already. But with that, I will end the recording.